I'm Alex, hi, and I will be providing an overview and introduction to Cabinetry. This is going to be a mix of slides and notebook material. And I think to make this the most useful, if you have any questions or comments at any point in time, just raise them, we'll go over them. If they'll get addressed later, we'll get back to them, but we can make this a bit interactive. I think that would be great and more interesting than me just talking for, I think, 40 minutes. All right, a disclaimer and a bit of context here. I'm working on Atlas, and that biases my view to some extent. I'm very curious if you're coming from different backgrounds to learn where your perspectives and use cases differ. So get in touch. I'm happy to talk this week about this. It's not a surprise, probably, if you hear that bin template fits such as the HistFactory model implemented by pyhf are widely used for inference, and typically they get rather complex in actual use cases. So we've seen now a pretty simple setup for the tutorial, just for the purpose of teaching you how things work. But in practice, you're going to be dealing with of the order of 10,000 histograms or so to build one of these models together. And you build these many times and you iterate, you debug your models, you understand the results, and you frequently modify what you're dealing with in order to get from the initial construction of a statistical model to the actual publication of your associated paper. To help with all of this, there's a set of tools that emerged over time. There's a ton of tools that are not publicly available, unfortunately. Some of the ones that are, I'm listing down here at the bottom. Popular in Atlas is HistFitter, for example, and CMS is Combine. And typically these tools help you construct workspaces and also help you deal with them and provide visualization and debugging utilities. Now, Cabinetry is a library that fits into this space as well. And it enables you to construct HistFactory models in the way that pyhf expects them, and to also perform inference on them and to provide utility that helps you deal with such models. It's part of scikit-hep, and it uses a lot of these Python libraries, part of scikit-hep, in order to provide all of this functionality. In practice, there's two different aspects of what you can use Cabinetry for. And the first of those is to build your statistical model. And the way you do this in Cabinetry is that you have a configuration, which is declarative, where you say essentially details about the physics model that you're trying to investigate. And then Cabinetry looks at that configuration. We'll see how it looks like in a second. And it translates that into the instructions for creating all these template histograms that are needed in order to produce a statistical model that you have specified. It then also gives you the HistFactory workspace that corresponds to your model. And that is then something that's ready to go to be used with pyhf together. So that's one aspect. You go from a declarative configuration to a statistical model ready for inference. The second aspect is actually performing inference and visualizing results and debugging the models that you're building. You can do these two independently. You can build a model with Cabinetry and then go on use it with some other software, or you can build a model with some other software and go on and use Cabinetry for inference, or use Cabinetry for both as well. The way that the configuration that I just mentioned looks like is shown here as an example. We'll see this again in the notebook in a second. This is serialized to YAML, but really it's just a Python dictionary, so there's no need to ever save this to a file if you don't want to. There's kind of like a block structure where there's some general settings, and then the different regions of phase space that you're fitting. These correspond to channels in pyhf language, the different samples that populate your phase space, including the data that you're trying to fit your model to. In the end, and there's a list of systematic variations here on the right. Again, this is a short example. In practice, this can be many hundreds of entries long, where you specify how to evaluate different sources of systematic uncertainties. And lastly, normalization factors. So, for example, your parameter of interest, some cross-section, and other things that you're measuring in your analysis. We'll have another look at this in a second in the notebook. And assuming that you have written this configuration, and this is something you need to do yourself, because here you specify physics and details about the physics analysis that you're intending to do. So this is something that can't be done for you. You do this by yourself. But once you have written this down, then Cabinetry takes that information and translates it into effectively code that tells you how to obtain all the different template histograms that are needed to now build a statistical model out of this. There's two ways of going about this. Either you give to Cabinetry just n tuples, so just columnar data, and Cabinetry builds histograms for it for you. The alternative is that you have externally built histograms yourself, for example, with coffee or really anything else. You can build those with IDF, you can build them in any way you want. And then you just ingest these histograms into Cabinetry so that Cabinetry knows where they are for subsequent workspace construction. As optional post-processing, I'm not going to go into detail here, but you can apply things such as histogram smoothing, and then you serialize everything to a JSON file. Or again, because this thing is just a dictionary before you hand it to pyhf, you can also just deal with this dictionary for this workspace. And usually what you want to do very early on as well is you want to actually visualize the thing you have built. So there's an example at the bottom. If you build some template histograms, you can plot those immediately to see that what you're getting out of this is a sensible distribution, really useful to catch bugs early on. Then there's lots of visualization utilities available to you. And if you see the slides here, there's some examples. Those are probably kind of familiar if you're working with profile likelihood fits. So you can see the distribution of nuisance parameter pools at the top here. You can rank parameters by their impact on the thing you're trying to measure, correlations, likelihood scans, parameter limits, as we've also just seen in pyhf and so on. All the standard stuff is available here for visualizations. The example here, again, we'll get back to this in the notebook, shows you that you can use Cabinetry to deal with statistical models that have been built with other pieces of software. So this example here is an atlas analysis that is published on HEP data. And you can download the workspace of this actual atlas analysis straight from HEP data. The code on the bottom here shows you how to do this. And then you can use Cabinetry to visualize how the distributions look like. You can perform fits and so on. You can try it out here via this link as well if you want to see how that works out. So any public atlas workspace, you can investigate it in this manner. And I think this afternoon we'll have more examples for how you can visualize aspects of workspaces that we have published. All right, so here's the full workflow. And showing you on this example sort of the conceptually the different steps in this workflow and also the pieces of software that we're using. So at the very left, first step is we generate histograms, all the template histograms that are needed. So either you do that by yourself or you use Cabinetry to steer the production of histograms for you. And what you get out of that is just lots of one-dimensional histograms ultimately. You serialize that to a statistical model, which you can save as JSON. Again, Cabinetry does that for you. Then pyhf comes along and takes that model and turns it into a likelihood function. So once you have that likelihood function available, you're free to minimize the negative log likelihood. iminui is an example of what you can use with this. There's other minimizers available in pyhf. And both of these steps, the construction of this function and also the minimization, can be wrapped with Cabinetry. So again, you can use higher level APIs provided by Cabinetry for this as well. And then after you've done your fits, you can then visualize inference results. Again, Cabinetry can do that for you. As an example here at the bottom, we'll see some more examples. So conceptually, that's how the workflow works. And what you'll see here is effectively for all these steps, you can do them using Cabinetry, but typically Cabinetry will call lots of other libraries in order to actually make this happen in practice. All right, on this slide here, I'll briefly talk about some future directions of Cabinetry, of where things are going. So in the short term, the main goal is really to address the backlog of open pull requests, especially those contributed by users, which are great. And I'm super thankful that there are these pull requests. There's a list here of some of those. And you can check out the pull requests are linked here. You can check them out. We'll see some of these things in action, particularly here, the creation of histograms in parallel. We'll see this in action now in a second, but there's lots of other improvements. So the really main goal is to actually get those all merged and release them in a new version. There's a few things listed at the bottom for the longer term. Automatic differentiation is a big item that will take some work, but it's one we're interested in to make that possible. Happy to talk in breaks and such about this. I won't go into any more detail here of what that actually means in practice. There's lots of feature ideas. There's again a link here if you're curious about this. But feedback here is very welcome. There's more features than there's time for. So to help with prioritization, any feedback is always super appreciated. And of course, if you have additional ideas and requests beyond those listed here, I mean, do get in contact. Feedback and also contributions are always welcome here. Now, given that I mentioned that there's more features than there's time for, the next question is, of course, okay, what about features that are not currently in Cabinetry? How do you deal with things for which there isn't an API that you can just use? And the problem here is essentially that some things are not available yet, but probably in scope, and they will be available at some point. Some other things are probably generally out of scope. And the reasoning for this is that we're trying to balance providing useful features, but also keeping everything maintainable. I've had some experience with other projects where providing lots of features makes maintenance very difficult. So the idea here is to strike a balance. And what this means is that typically, I think it's a good thing if a user can write a few lines of code, and that can make the assumptions that they have beyond the thing that they're doing very explicit, because they're writing these assumptions down explicitly in code. And if they can still achieve their goal, then that's fine. So the idea is not necessarily to provide a black box function that does a lot of things, but to provide a number of different functions that helps you do these things that would otherwise be annoying. So there's some examples here. And hopefully then, whenever you need something that is not immediately available, there's at least a few pieces of API available that help you make the thing you're trying to do easier. I'm very happy about to hear about feedback as well. And given that sometimes then you still might be wondering, okay, I have this problem that I need to solve and I don't really know how to get started with this. I started to collect examples for how to do certain things in a dedicated place on GitHub. You can see that linked here. Hope to grow this further in the future, which just shows you examples for how to achieve certain things where you don't just call a single function, but you need to do a few things. And hopefully that can help also showcase how to do similar things yourself. And again, always happy to discuss about requests here. The scope isn't set in stone. So I'm very happy here to talk about these things. All right, so in summary, Cabinetry is a Python library that helps you create statistical models and operate with them using tons of tooling in the Python high energy physics ecosystem to enable all of this. And it is more of a library than a framework, while some of the comparable tooling, I think, leans more on the framework side, which means that sometimes you have to write some lines of code, which is by design and hopefully makes things a bit less black box and more flexible, and also from a maintainer perspective, more maintainable. All right, with this, we'll jump over to a notebook. If there's any general questions or comments, I'm happy to address them right now already. Oh yeah.
Multi-dimensional histograms are also supported with this?
They are not. The limitation here is mostly the HistFactory model itself, which deals exclusively with one-dimensional histograms. You can sort of work around this by, if you have like a two-dimensional histogram, for example, you slice one dimension into different channels and then have multiple one-dimensional histograms. That's not fully the same, and there's places where this is going to give you different results, but conceptually, that's what people do.
This, for the reasons that Alex just said, this is like one of the things that when considering doing a like refactor for a HistFactory v2, this is something that is already kind of like in scope to discuss, but this is something that will not just be like a few people talking about, but we're going to need broad community engagements to redefine like what the HistFactory model formalism is. So, which, yeah, we'll have some related discussions this afternoon regarding the HS3 as well. So,
what are the limiting cases where in 2D you get different results than if you just flatten?
Right. Okay. So a lot of technical things. When you do smoothing, for example, you would smooth a 2D space where you have some reason to assume that they're physically related in a different way than smoothing one-dimensional. Also, systematic variations. We have templates right now that vary your one-dimensional distributions in some way. And all of the variations are always varying one parameter at a time. And in 2D, you would again have a different way in which you vary things all at the same time. Because if you have some sort of 2D distribution and you vary in that 2D space, that's not necessarily the same as varying independently in the one-dimensional space. Because of the way we split in cabinetry normalization variations and shape variations into 2 pyhf modifiers. That's a bit technical. We can talk more about this in a coffee break.
That would have been my next question.
To make this more clear.
Yeah, we can talk about it.
Yeah.
Okay. Yeah.
Carsten?
Yeah, I have a, let's say, a bit technical question on the way you make the histograms, because so I come from Atlas also, and I have a lot of experience with libraries that do like high-level histogramming stuff. So my main question is like, what type of inputs do you accept to make histograms?
And tuples, which right now have to be root files. This could be relaxed, or histograms themselves, which right now have to be th1s and root files.
Okay. And what about all of these derived formats like DAOD stuff with?
No, right now it has to be flat and tuple. We're reading with uproot. You can work around this. There is a function that allows you to hijack the histogram production process and essentially say, here's my own code that will read out the file. So if you write a few lines of code, then you can in principle use that infrastructure to read something else as well.
How difficult would it be to plug in root data frame as a backend?
Probably not too difficult. I have not tried that out. Conceptually, if you have root available in your environment, it shouldn't be too much work. There's an example I have which is using coffee instead, which conceptually is very similar. It's just something else to like go through. So conceptually it shouldn't be too hard, I think.
Okay, thanks.
All right, we're good. I think we can continue.
Yeah, copy schema should get you most of the way there, at least for sure for the CMS side. But for the Atlas side, there are some things missing that we're still trying to figure out. That's an ongoing thing happening, at least in Atlas. For other experiments, I think that's going to be sort of depending on what those experiments are doing. So there's not a general one thing fits all approach.
All right, so the second half here is going to be a notebook where we'll take a look at some things in practice. In the repository that's linked to the contribution on Indico, if you go to the GitHub repository, you'll see links to Binder Hub, either on my binder or on the SSL, where you can open this and you can follow this along as well, if you're interested.
Make it like one size bigger.
Yes, the font. Yeah, with this, okay. Note we're using not a released version of Cabinetry here. We're using a specific branch just to demonstrate one feature. Hopefully this will be in a release very soon. Turns out that things are more complicated than expected there. Again, happy to talk in a coffee break for why this isn't released yet. All right. Okay, we get started. We import Cabinetry. Cabinetry does output via the Python logging module, which you can configure in any way you want, depending on how verbose you want the output to be. There's a sensible default, sensible in my opinion, provided you can configure it in any other way if you want to instead. We're going to be using a number of libraries, so we'll just import all of them. We'll deal with them as we come across them. Okay. First part in this notebook is we're going to be building a statistical model, one of the features that Cabinetry helps you with. To build one, we need to first define the model that we want. The configuration that we're building here, in this case, is not going to be just reading some external YAML file, but we're just building this dictionary object from scratch. And you can see the settings that we're going through. I won't go through every setting in great detail here, but again, happy to talk about all of those. So there's a few general pieces of information you need to provide. You need to say, for example, where do I find the files that I'm going to be reading in order to be producing my template histograms? So in this case here, we're just reading n tuples and they're provided at this place. This thing here in these curly brackets is a placeholder. You'll see this again in a second. And then we also need to say which regions of phase space are we dealing with, and the region of phase space has a name. It also is defined by some filter. This is just a toy example here, so don't interpret the left-hand chart here too much. But we have this region of phase space defined by this filter. We have the observable we want to be fitting and a binning for that observable. So here there's just a single region. This is a list, so this could be many regions of phase space as well. Then we need to be dealing with different samples as well. These samples crucially need to have information for how to access them. So in our case, if you look at this repository, there's an input folder, and then there's some root files in there. So for example, for the signal sample, this shows you the place where this can be found. And then the signal is living in a tree, and it has some weight associated to it. So the weight here is just called weight, is what this is saying. And then the background is living in a different tree. So there's different structures here for how your input could look like that are supported. Hopefully this is sufficiently generic. If there's any kind of setups of your input structure that are not supported, please get in touch. I would be happy to generalize this. Starting out, we're not adding any systematic uncertainties at all to our model. So this is just an empty list here for systematic uncertainties. And we define a single normalization factor, which is going to be scaling our signal in a range from -5 to 10. There's configuration validation available. There's a schema telling you how this configuration is supposed to look like. So if you did anything wrong already at the beginning, then this will complain because you have defined then something that Cabinetry doesn't understand, which will subsequently cause issues. So you can check that what you have defined at least satisfies the schema that the configuration has to satisfy. There's also a way to look at an overview of what you have written down in your configuration, 3 samples in one region of phase space and 1 normalization factor. All right, so we have this dictionary object now that we call config, and we are now interested in turning all of this information into template histograms to create a statistical model. You can do this by just calling this function here, and that does everything for you behind the scenes. It tells you a bit here in the output what exactly it's doing. It's reading some input data and it's saving what it has then produced, the histograms, to a new file for all the different histograms that need to be built in order to build the model that you have specified in your config. These histograms are saved now in a folder here. Now, in practice, here we're just building a handful of histograms, but in practice, you're going to need many, many histograms. So you will want to parallelize this in some way. And this is where this branch comes in that provides you an interface to be doing that. The idea behind this is that you will get from Cabinetry now a list of instructions, and these instructions say what is needed to build any of the histograms that you need. So in practice, when I run this, this is a new function added by this branch that we're using here. You get a list of instructions, and then in this case here, just 3 different instructions that are printed at the bottom. Those are tuples of dictionaries, and these might not make a lot of sense, but you might recognize some pieces in here. There's a filter, for example, so that's something that certainly for histogram you'll need. You need to figure out which data to access. There's the observable, there's the binning. So all of these just tell you implicitly information about a histogram to be built. Once you have this list of instructions, and again, in practice, this can be like 50,000 entries long, then you can take pieces of these instructions and really send them off and distribute them, parallelize them in any way you want. So this is kind of up to you as a user then to use your preferred method, sending this to a batch system running on one gigantic local core where you can multiprocess or really anything else. In our case here, we're going to be using Dask for this demo. So we're spawning a Dask cluster, and we just distribute the production over that cluster. We send in this list of templates, and then we have this helper function, which effectively just calls again this templates build interface with, as an argument, a single template instruction at a time. So here we're just building in parallel jobs, 1 different template at a time. In the beginning here, we delete the histogram outputs, and then we look at the folder again, just to demonstrate to you that indeed this works. You'll see some output here from Dask, and we will see that we have histograms at the very end. So we have deleted them and we have rebuilt them, now distributed over Dask. In practice, if you have lots of resources behind your Dask cluster now, you can scale this very far and produce everything in parallel. There's a post-processing step here. This is optional. This is where you would apply things like smoothing, for example. I'm not going into more detail. At the very end of the notebook are some bonus material sections, which I won't have time to go over in this talk. You're welcome to have a look, and I'm happy to talk more about them this week as well. And once we have built our template histograms, it's a good idea to look at them just to see that what we have built makes sense, that we haven't made some bugs, for example, where we scale our luminosity by an order of magnitude wrong or something. So here, this looks pretty sensible. We see our two samples here. We see some pseudo data and just this one region of phase space that we have defined. All right, then the next section here adds systematic uncertainties to our model, because so far our model didn't include any of them. And this shows you how to define systematic uncertainties. So a fairly straightforward one is a luminosity uncertainty, which just changes the normalization of your Monte Carlo-based predictions by 5% up and down. And then there's some other uncertainties here where kinematics of objects change, for example. So there's a modeling uncertainty for our background, for example, where you now look in a different tree in order to build these predictions, which is a very common thing in Atlas, where you have multiple different trees that all contain different amounts, different types of events that are processed in different ways. So there's systematic uncertainties you can define in this manner. Because we have now added to our config, so we have updated our config dictionary object, we have added additional information. We need now, if we want to build a statistical model, histograms corresponding to these extra things we have specified. So we're going to be running these steps again in order to build all of the histograms so that we are ready to convert all of this now into a statistical model with this extra, with these extra variations that we have defined. You can visualize things again. And here specifically, we're visualizing the templates corresponding to systematic variations. And this is showing you the systematic, we call it modeling, where we have some nominal distribution. This just in black, that's how our background looks like by default. And we have in blue a variation of this nominal distribution. And you see here, in this case, this is like what you would call a two-point systematic. So we just have one alternative prediction. And then in practice, what we would do with something like this is we would symmetrize this in order to have a nuisance parameter that allows us to continuously shift from our nominal prediction to an alternative in a positive and negative direction. Right, and there's another example here of another type of variation. So these kind of plots are usually very helpful to just sanity check that the variations that you have defined are sensible. Again, this is a place where easily bugs can happen if you make a typo or something. So this is an important thing to sanity check. Okay, we have histograms available. So let's build a workspace out of them. And the way to do this is you just call the function cabinetry. You hand again over this configuration object that contains all the information about the model you're trying to build. And you get a workspace out of this. You can optionally save it to file. So this is what's happening here. And then as we've just seen, this workspace is really just an object you can serialize to JSON. And that's what's done here. You see how the workspace looks like. I won't go into more detail. We've just seen this a second ago. You'll see this one is slightly more complex than the one we've had before, but still very minimal. So in practice, these things can easily be thousands of lines long for a full-scale model. Because at some point, the structure of this becomes not that easy to interpret if you just look at thousands of lines of JSON. You might want to look at the structure in different ways. You might want to visualize it. There's one somewhat recent addition which helps you with this, which is this thing I call modifier grid. And what this shows you is it shows you sort of these kind of tables for different regions of phase space and for different samples. And then for different parameters here on this axis that is going horizontal. And what the different colors correspond to is the types of modifiers that are acting on this combination of a sample and a parameter. And this helps you because you see sort of the structure that your workspace has. And oftentimes this can reveal, for example, issues in your definition of the model. So if you see places that are white that you wouldn't expect to be white, for example, then that might indicate an issue. So our example here is pretty simple. So there's not so much structure that you see here. So I attach a bigger one from an Atlas workspace on HEP data. And down here, you start already to see more structure, right? You see lots of areas of yellow here. And then you see some places in here that are white, for example. So on this single top sample in the middle here, for example, there's lots of white. So now you might ask the question, okay, why is this white? Why are all these parameters where there's hysteresis modifiers on the other samples, why are they not acting on single top variations? So now you can look at this and you can ensure that this is not a bug in your definition of the statistical model, but that's really intended. So as the examples get larger, the workspaces get larger, this becomes more helpful in order to debug what's going on. All right, let's perform some statistical inference. We have our specification for the workspace, and we can extract from this our model, our PDF, and the data we're trying to fit. This data is just a list of floats. We've just seen this in the previous talk as well. Now we can use Cabinetry to perform a fit. What this does ultimately is just it wraps the pyhf interface for doing a fit, and it saves everything into this object called fit results that you can use to then, for example, visualize the results. You get a summary of the best fit parameters at the very bottom here. And this fit results object just has multiple different cells. For example, it has labels, the names of all the parameters, the best fit results for the parameters, the uncertainty, and so on. So you can just inspect what's in this fit results object in order to access all of these numbers. But usually a very helpful way, if you have lots of parameters, to deal with them is to visualize everything in these kind of common ways in which we tend to do this. So the so-called pull plot here at the bottom, for example, is one of those. Again, here, this is a simple example, so there's only 3 entries. In practice, this can be many tens of entries long. So this is an example where you just hand over this fit results object to the cabinetry.visualize module, which contains functionality to show you how these things look like in a more visual manner. There's other examples for visualizations available, correlation matrix, for example. This can become very large. So there's some handy functionality like a pruning threshold, where you only keep parameters in this matrix if they have at least a certain correlation with any other parameter in the fit. Then when you perform fits, what you also want to do is you want to look at how your model looks like after the fit to data has been performed. There is an API here called prediction in this model utils module. And this API effectively calculates for you the prediction of a model, including all uncertainties on the model with their correlations correctly taken into account. And the example here is pre-fit, before a fit has happened. You see pretty large uncertainties on our model before we have fitted to data. Before we get to the post-fit one, I just want to mention you can change the way these plots look like. So for example, if you want to change the colors of the different parts of your histogram here, you can do so. These are just the matplotlib color names that you can pass in here in order to like change colors. And you can also operate on this matplotlib object. So if you want to set, for example, the nice LaTeX title here for the axis, you can do so. You can just use standard matplotlib API to achieve that. Instead of just plots, you can also create tables. There's different formats available for these tables, including LaTeX. If you want to dump them somewhere, there's different types of tables available. And they also get automatically saved to disk to further keep them. If you want to have post-fit results, we had this fit results object containing the result of your maximum likelihood estimate. You can pass that into this prediction API, and now you have a post-fit result available to be visualized as well. You'll note compared to before that now the uncertainties here of your model post-fit are much smaller as expected. Some other features here. Typically, you will be looking at Asimov data in order to evaluate your sensitivity before you unblind the analysis that you're performing. There is a function here available for you to create this Asimov data set, and then you can also perform fits with this. As a feature by design of this Asimov data set, you will see now when we fit to it, all of our parameters here are either 0 or 1, just at their expected maximum in the fit, which is by design of this data set. And as I mentioned previously, this does some assumptions of what to do with free-floating parameters. It sets them to the value that is specified as their initial value. So this is how you can configure what you expect, for example, your signal to be like, what you would like to be like in the Asimov data set. So but here it's just set to 1. Quickly flashing some other pieces of functionality. The fit API in Cabinetry provides you other features to quickly get different kinds of functionalities. So if you want to get discovery significance observed and expected, you can just run this significance API. And again, if you want to get parameter limits, there's also an API for that, which performs a scan over your space of the parameter of interest in order to find the crossings of the CLS value with 5%. You'll see here it does all the different scans in order to find these crossings for the observed and expected scenarios, and then like visualizes all of this to show you here the distribution, including the uncertainty bands. Okay, I think we don't have time to look over this example of this atlas analysis. You're welcome to run this by yourself in order to show how you can take this published atlas analysis, you can download it from HEP data with pyhf, and then you can visualize all of these results. You can perform fits with Cabinetry as well. There's a lot of bonus material at the bottom. I don't have time for this. I just want to highlight one thing. There's a command line interface. You can check it out. And this shows you some of the available options here. I personally find this quite useful when dealing with workspaces. If you want to quickly inspect them, you can just use the command line interface and point to a workspace. Yeah, and I think that's everything I have. Happy to answer any questions. If there's other questions, I'm around this week, and I'm around generally at CERN, so just feel free to get in touch. Thanks.
All right. Thanks very much, Alex. That was great. Okay, so let's go first to Zoom to see if there's any questions. I don't see any raised hands, so maybe let's go to the room next. Yeah, Lorenz.
Yes. Can I ask the question about how you split your modifiers now? So this is what we touched on before.
Yeah, you absolutely can ask that question.
Yeah.
Yes.
So why is it so why did you choose to make it so differently to pyhf?
Okay, so it's not different to pyhf. It is using pyhf functionality, but there's a choice to be made. So this shows what we're talking about. I'm sorry, this is going to be a bit technical now. Okay, so if you in pyhf, there's something called the histosys modifier, and
For the what?
histosys. It says here this thing, histosys, and this modifier is meant for varying your nominal prediction and to some other prediction that you provide in all the bins, like an expectation in all the bins. Now, what happens if you use this modifier in pyhf is that the interpolation and extrapolation between the nominal and the up and down variations is linear. So this is shown here on the left. So the parameter value, the nuisance parameter, is on this axis, and the yield predicted in each bin is on this axis. Nominal is at 0, the plus minus variations are at these plus minus points, and then these are just 2 bins in this example. And you see this is linear. So the problem with this is, with a linear extrapolation, that at some point, if you pull far enough, you're going to be predicting a negative yield, which is unphysical. So that's an issue if the variations have lots of change the normalization by a lot, because then your model will predict negative numbers somewhere, and that's going to crash your fit. There's a pyhf API to protect against it, but it's ad hoc. It's not great to use that instead. So instead, there is something now called the normsys modifier, which only changes normalization. And it changes that coherently for all bins in your channel. The normsys modifier is implemented with an exponential inter and extrapolation. And because it's exponential, the normsys modifier itself can never make your prediction of a sample go negative, no matter how far you pull it, because it will just asymptotically go towards 0 in one direction. And the normsys modifier can only deal with all the bins in a correlated way in one channel. So when you have now the case where you have a nominal prediction and some other prediction, which gives you different counts in each bin, what Cabinetry does is it looks at the overall normalization effect and in that region of phase space, and it plugs that normalization effect into a normsys modifier in pyhf. Then there's still the shape component left over, and it packs that into a histosys modifier and correlates these 2 modifiers. They're controlled by the same parameter. So that's the example at the bottom. You still will, your model prediction will still go through all the templates to the variations at plus minus 1 sigma by construction, but you see now that the behavior here towards 0 is much better. You asymptotically only go towards 0, so you protect against this predicting something negative and unphysical. This doesn't fully protect. You cannot fully protect against this, but it's much, much safer overall. So this is why this is done this way. However, now, coming back to the actual question, why this now matters for 2D, this is a choice for making the split. And implicitly here in the split, we say that we care about what's happening in one channel. So this channel now is the thing where we attach the normalization modifier to this channel. It would be different if we had like a 2D space, because it would be a different normalization factor in this 2D space. So each slice in the 2D space, if you want, might have a different normalization effect. So if we were to do the same or like an analogous thing in 2D, it might look slightly different. Or if we were to like slice one way or the other way, it would again look slightly different. But here we're talking purely about implementation, right? There's not really any physics here because we only have these variations. So there's no right or wrong necessarily. But this is how things are implemented. And then in practice, you may see slightly different results depending on which direction you slice.
That sounds like a smart way around protecting against negative fields. So why doesn't pyhf use that as a default?
pyhf only provides, I mean, you're free to use pyhf in any way you want, right?
Yeah.
And I don't think it's wrong for pyhf to allow you to have normalization in your histosys modifiers as well.
Sure, yeah.
So I think this is on the user for what to do. Maybe it should be more known.
Yeah.
Because I think it's a sensible thing, but yeah, sorry.
Yeah, no, I think Alex did a very good job of summarizing kind of our position is that we really want to take the position of a library that lets the users do whatever they want to do as, you know, like kind of consenting adults. But it's definitely something where, you know, we welcome feedback and there can be discussion and changes in future releases, so.
I mean, it seems like a nice kind of feature to have, even though you're not forced to use it, right? But to split up the modifiers in that way, it seems like a sensible thing to do.
Yes, I agree. I'm looking, okay, I don't have the link here. I have a tool somewhere that ingests the workspace and like splits things for you. If you have something where you don't have that split. So in principle, that's something that's not complicated to go from one to the other. But ultimately, it's a choice, and yeah. And Cabinetry is opinionated in that choice. So Cabinetry will actually not allow you to not split. So you have to kind of work against Cabinetry if you want to like achieve that. So it's not so easy. Yeah.